Okay, and hello and welcome to AS Level Physics with me, Will Kulbicki. Today we're going to be looking at fundamental particles, and we're going to learn that protons and neutrons are not fundamental particles since they consist of quarks. So previously we would have probably learned that protons and neutrons were as small as it gets. Turns out that's not the case. So now we're going to find things that are a little bit smaller than protons and neutrons. We're also going to be able to describe a simple quark model of hadrons in terms of up, down, and strange quarks and their respective antiquarks. We're also going to be able to describe protons and neutrons in terms of a simple quark model. So again, similar to that point B. D, appreciate that there is a weak interaction between quarks, giving rise to beta decay. Okay, so there's other forces at play when we go down to the atomic scale. And this is what causes various radiations to be emitted. E, describe beta negative and beta positive decay in terms of a simple quark model. Well, we've encountered beta negative before. We know that that is an electron, and beta positive is what we'll find is the antimatter equivalent of an electron, and we'll dive into that later. F, appreciate that electrons and neutrinos are leptons. So two different types of leptons there. Let's jump straight into it. Okay, here is a tree diagram of what we call the standard model. So when we get, this is what matter is made up of. We've previously learnt in GCSE that matter is composed of atoms, and atoms are made up of protons, neutrons, and electrons, being the protons and neutrons make up the nucleus. Now we move into AS, we're finding, hang on a minute, protons and neutrons aren't as small as it gets smaller. So let's have a look. Well, we can see that here in the diagram, subatomic particles can be divided into two categories. Leptons over there on the right-hand side, and if we just click, hadrons are on the left-hand side. Hadrons themselves are composed of two categories, baryons on the left and mesons on the right. So baryons, which are composed of 3 quarks, and mesons, which are composed of 1 quark and 1 antiquark. So let's have a look at baryons first. Baryons, and now we finally get to what we're familiar with, protons and neutrons. And a neutron, we can see there, is made of an up and 2 down quarks. Now here we can see that protons are made of 2 ups and a down quark. Now, this may seem silly, but the way I remember this is that neutrons has a U in it, which means that it's only 1 U. Protons has no U's in it, and that means it's 2 U's. That's just, doesn't make a whole lot of sense, but that's just the way I remember it. Neutrons, 1 U, so that's 1 UDD. Protons, no U's, so that must be the other one, which is UUD. So you may be saying, well, what is UUD and what is UDD? Well, these are just types of quark. Quarks come in many different, what they call flavors, but we say up, down, and strange. These are the only ones we need to know, and really we only need to know up and down at this point. We can see that leptons on the right, they can be divided into electrons and also neutrinos. So that's important when we come to later, when we come to balancing beta decay equations. We can see that neutrinos and electrons are of the same category. Here we have something called mesons, and this is in the syllabus, but it doesn't come up that much. We just need to remember mesons are 1 quark and 1 antiquark. Now you might be saying, well, what is an antiquark? Well, it's quark is quark is matter, and everything we know has an antimatter. Um, when matter and antimatter meet, they annihilate each other and give off gamma radiation. In this case, we have one quark and one antiquark that makes up a pi positive meson there. Okay, and we can have a look at antiproton and antineutron there. Obviously, they're just made up of the anti-quarks rather than just the quarks themselves. Okay, let's have a look at some key features of radiation here, just to remind ourselves. Well, we've met alpha particles before. We're familiar with those. Alpha particles are just helium nuclei. That means they have a nucleon number of 4 and a proton number of 2. So a charge of +2 and a mass of +4. We can say that they have a typical speed is slow, 10 to the 6 meters per second, bearing in mind that 3 times 10 to the 8 is the speed of light. A little slow for radiation. We can see if we drop down to beta negative particle and we look at the symbols there. Beta negative particle is sometimes just known as beta. It's also known as beta negative, and it's also known as electron because it is an electron. You see there? Nucleon number 0 and a -1 for an electron there on the proton number. Okay, we know that a relative mass of an electron to a proton is 1/1840. So it's 1840 times smaller or less massive than a proton. And the charge is -e. And we can see that they move fast at close to the speed of light. Beta positive particle is exactly the same as an electron, but it's a positron. It's antimatter electron. So properties are the same, except opposite. Gamma ray, we know that that type of radiation is electromagnetic, so it travels at the speed of light. Okay, so some key issues here that we might want to consider. Obviously, I'm just going to try and move that. Oh, okay, that's fucked it. Move that down there for now. Radiation arises from unstable nuclei. Alpha radiation arises from unstable nuclei which have too many protons and can no longer be balanced with neutrons. So if we think of the nucleus of an atom as containing neutrons and protons, and these seem to increase as the atoms get bigger. The number of neutrons match the number of protons. But then when we get bigger and bigger atoms up to numbers greater than 83 protons, then there are so many protons in the nucleus of the atom, protons and neutrons, that it's become unstable. Now, why has it become unstable? Well, there are two forces at play to consider here. One is the electrostatic force, and that is that force that we've met previously, which is the force between positive and negative charges. And there's another force at play called the strong nuclear force. Now, if you think about a nucleus, it only has positive charges, so we know that positive charges repel each other. So why doesn't a nucleus just blow itself apart? Well, that is because of a thing called the nuclear strong force, which binds protons and neutrons together. Of course, but at some point, if you keep adding positive charge, the electrostatic force is going to become too strong for the nuclear force. In which case, this is what happens when we when we get to a certain size nucleus, and then they want to emit alpha particles to try and restabilize themselves, and that is when we get radiation or radioactive nuclei. Also from this, we can also see that the last point there is beta radiation is a result of what we call the weak nuclear interaction, and this is another force at play, and this is responsible for protons or a neutron giving out beta radiation. Okay, so what is beta decay then? Well, beta decay is the process by which a neutron becomes a proton, an electron, and an antineutrino. Okay, and here we can see by the equation, beta minus decay is a neutron changing to a proton, and at the same time it's giving out an electron and an antineutrino. So we have to think about what is going on there. How can a neutron change into a proton? Well, we have to think of a neutron as being able to have both positive and negative charges inside them. So a neutron can give out a proton, can change into a proton, but then it's missing half of its balanced charge, right? So in order to balance that, it needs to give out an electron. But we can't give out an electron without giving out an antineutrino, which is an anti-lepton, in order to balance that. So we can think of an electron as being a lepton and an antineutrino being anti-lepton. So everything is balanced in that equation. I'm just going to move myself up a bit and continue. Beta positive decay is the process by which a proton becomes a neutron, in which case a positron and a neutrino are emitted. So in this case, proton is becoming a neutron, in which case a proton is giving up its positive charge in order to become that neutron. It's giving up the positive charge by giving out a positron. But we can't just give out a lepton. We need to balance that with another lepton, which is what we call the neutrino in this case, bearing in mind that a positron is an antineutrino. And there we have it. These equations